Deep in the frigid outer reaches of our solar system, far beyond the familiar planets, drifts a world shrouded in shadows and secrets. Varuna. This enigmatic dwarf planet, hidden within the distant Kuiper Belt, holds mysteries that challenge everything we think we know about the formation of our cosmic neighborhood. Imagine a place so remote that sunlight takes hours to reach its frozen surface, where temperatures plunge so low that gases freeze solid, and where ancient clues about the dawn of our solar system remain locked in ice. This isn't science fiction, this is Varuna, a celestial puzzle waiting to be solved, and today we're embarking on an extraordinary journey to uncover its 25 most baffling enigmas. What makes Varuna so captivating isn't just its distance or its size, it's the sheer number of unanswered questions that surround it. Why does it spin so rapidly, completing a full rotation in just under 6 hours? How did it acquire its strange, elongated shape? What mysterious forces have sculpted its surface over billions of years? Each of these puzzles invites us to look closer, to question our assumptions, and to marvel at the complexity of the cosmos. For astronomers and space enthusiasts alike, Varuna represents one of the most compelling frontiers of modern exploration, a reminder that even in our age of advanced technology, the universe still guards its secrets fiercely. As we journey through these 25 unexplained mysteries, you'll discover why Varuna has become such a focal point for scientific curiosity and wonder. From its peculiar composition to its gravitational interactions with other Kuiper Belt objects, each mystery pulls us deeper into the story of our solar system's formation and perhaps even the origins of life itself. This isn't just a list of facts, it's an invitation to explore, to question, and to feel the same awe that has driven humanity to gaze at the stars for millennia. So settle in, open your mind to the possibilities, and join us as we unravel the secrets of one of space's most mysterious worlds. Our first mystery takes us to the very spin of this distant world, a characteristic so bizarre it immediately sets Varuna apart from most of its neighbors. While many large objects in the cold, dark Kuiper Belt take dozens of hours or even entire Earth days to complete a single rotation, Varuna whips around at a breathtaking pace. It completes a full turn on its axis in just 6 hours and 20 minutes. To put that into perspective, our own planet Earth takes 24 hours for one rotation, and even the larger, more massive Pluto spins at a far more leisurely pace of over 6 days. This rapid spinning presents a fundamental puzzle for planetary scientists, as an object's rotation is a direct echo of its past, a fossilized record of the forces that shaped it during the solar system's violent infancy. The primary question is, what could have imparted such tremendous angular momentum to this frozen world? One leading theory points to a history of violent collisions. In the chaotic early days of our solar system, the Kuiper Belt was a shooting gallery of protoplanetary debris. It's plausible that a colossal impact with another sizable object could have struck Varuna a glancing blow, effectively winding it up and setting it into this incredibly fast spin, much like how a billiard ball spins after being struck off-center. This scenario, while compelling, is difficult to prove and raises further questions about what happened to the impactor and why Varuna's surface doesn't show more obvious scarring from such a cataclysmic event. Another fascinating consequence of this rapid rotation involves the object's very shape. The immense centrifugal force generated by spinning so quickly would have actively sculpted Varuna, pulling its material outward along its equator. This force is likely the primary architect behind its highly elongated ellipsoid shape, resembling a stretched-out watermelon rather than a perfect sphere. This shape tells us that Varuna is not a rigid, solid body of rock and metal like the inner planets. Instead, it must be a relatively malleable mixture of rock and ice, a rubble pile held together by its own gravity, which was able to deform and flow under the strain of its own rotation over billions of years. This insight into its probable internal structure makes its rapid spin even more astonishing, as such a loosely bound collection of material could theoretically fly apart if spun too fast. The fact that Varuna holds itself together is a delicate balancing act between gravity and momentum, a dance that began when the solar system was young and continues to this day in the profound silence of deep space. Building on the puzzle of its frantic spin, we now turn our gaze outward to the path Varuna carves through the cosmic dark, a trajectory that is every bit as peculiar as its rotation. While many large Kuiper Belt objects settle into relatively circular, predictable orbits, Varuna follows a far more dramatic and elongated route around the Sun. Its journey is a constant swing between two extremes, swooping in as close as 40.9 astronomical units from the Sun at its nearest approach, only to swing back out to a distant 45.3 astronomical units at its most remote. This 6 billion kilometer difference between its closest and farthest points creates a profoundly elliptical orbit, a characteristic that marks it as an outlier and points to a history shaped by immense gravitational forces. An orbit this stretched is a telltale sign of a dynamic and disruptive past. In the pristine, early solar system, planets and dwarf planets are thought to have formed from a thin disk of gas and dust, naturally leading to more circular orbits. A highly eccentric path like Varuna's suggests it was not left to evolve in peaceful isolation. Instead, it was almost certainly gravitationally kicked or scattered by a massive perturbing force. The most likely culprit for this celestial shove is the gravitational influence of Neptune. As the giant planet migrated outward in the solar system's youth, its immense gravity would have acted like a cosmic slingshot on countless smaller objects in its path, hurling some inward toward the Sun and flinging others, like Varuna, into these wild, stretched-out orbits. This theory places Varuna as a key witness to one of the most significant events in our solar system's history, the great planetary migration that sculpted the outer reaches. This elliptical journey also has profound implications for the world itself. As Varuna travels along this lopsided path, its distance from the Sun's warmth varies dramatically, subjecting it to significant changes in solar energy receipt. This likely drives complex seasonal cycles on its surface, potentially causing ices to sublimate and recondense in a slow, rhythmic dance over its 280-year-long orbit. Furthermore, its changing position relative to Neptune means its path is not entirely stable over astronomical timescales. Gravitational interactions with the ice giant could subtly tweak its orbit over millions of years, adding another layer of complexity to its long-term evolution. This dance with a giant highlights Varuna not as a static relic, but as a dynamic world still engaged in a gravitational conversation with the solar system at large. Adding to the enigma of its orbit and spin, the third great mystery of Varuna confronts us with a simple yet profound visual paradox. This world is incredibly dark. In the vast, sun-starved expanse of the Kuiper Belt, most sizable objects manage to reflect a modest amount of sunlight, often appearing as muted, grayish spheres to our most powerful telescopes. Varuna, however, stands in stark contrast. Its surface possesses an albedo, a measure of how much light it reflects, of a mere 0.04 to 0.06. To grasp just how dark that is, picture fresh asphalt on a road. Varuna's surface is nearly as black, reflecting back only a tiny fraction of the already feeble sunlight that reaches it. This makes it one of the darkest known substantial objects in our entire solar system, a characteristic that immediately signals something unusual is coating its frozen exterior. This profound darkness is a direct clue to the composition and history of the surface material itself. Ices like the water ice or frozen nitrogen found on brighter worlds like Pluto or Eris are highly reflective. If Varuna's surface were predominantly clean, fresh ice, it would shine much more brightly. the fact that it doesn't suggest its surface is covered by a thick, dark blanket of other material. Planetary scientists point to two primary culprits for this cosmic soot. The first is the long-term buildup of complex organic compounds, often called tholins. When simple ices like methane or nitrogen are bombarded by cosmic rays and solar radiation over billions of years, they can undergo complex chemical reactions, polymerizing into dark, reddish-black, tar-like substances that are excellent at absorbing light rather than reflecting it. The second possibility is that the surface is simply ancient and has been thoroughly space-weathered. In the absence of any geological activity to renew the surface, a constant rain of micrometeorite dust and the relentless implantation of particles from the solar wind could have gradually created a dark, uniform layer on top of any primordial ice. This leads to a critical and unresolved question. Is Varuna's surface dark because it is very old, and this dark coating has had ample time to accumulate? Or is its fundamental composition just inherently different from its brighter neighbors? The answer could redefine our understanding of the Kuiper Belt's diversity. This mystery of the dark surface is inextricably linked to the puzzle of its rapid rotation. That frantic spin means that any given point on Varuna's equator is moving at a significant velocity. This would make it exceptionally difficult for any light, volatile ices to remain stable on the surface. If a patch of frozen methane, for example, were to sublimate into gas from the weak heat of the distant sun, the resulting vapor would likely be lost to space entirely rather than being redistributed and refrozen elsewhere on the surface, as happens on more slowly rotating bodies. This process could effectively strip the world of its bright, reflective ices over time, leaving behind only the darker, non-volatile rock and complex organics to dominate its appearance, creating the profoundly dark world we observe today. This bizarre and elongated shape forms our fourth great mystery, a visible defiance of the cosmic norm. For a gravitationally rounded object in this size range, we expect a world that is essentially a sphere, its own self-gravity having long ago pulled it into the most efficient and relaxed shape possible. Planets and large moons are round for this very reason, but Varuna is different. Detailed analysis of its light curve, the subtle changes in its brightness as it rotates, reveals it is not a sphere. Instead, it is best described as a triaxial ellipsoid, a stretched-out shape resembling a rugby ball or a watermelon, with three different axes of different length. This significant elongation is a direct and puzzling contradiction to what our models predict for such a body, forcing us to reconsider the very nature of its construction and history. The key to this mystery lies in the delicate balance between two powerful forces: gravity, which works to pull everything into a spherical ball, and centrifugal force, generated by its rapid rotation, which tries to fling material outward at the equator. For most large objects, gravity wins this tug-of-war hands down, but Varuna's incredibly fast 6-hour spin tips the scales, creating a centrifugal force so strong that it successfully bulges the equator and elongates the entire world. This tells us that Varuna's internal structure cannot be a solid, rigid ball of rock. If it were, its own gravity would not be strong enough to deform it into this shape against the material's own strength. Instead, it must be a relatively malleable, deformable body. This points toward a specific and fascinating internal model. Varuna is likely what planetary scientists call a rubble pile object. It's not a single, solid chunk of rock and ice, but rather a loose collection of countless smaller pieces, all held together by their collective, but relatively weak gravitational attraction. Think of it not as a bowling ball, but as a bag of gravel spinning rapidly. The bag and its contents can easily be pulled into an elongated shape without breaking apart. This rubble pile structure suggests Varuna is a survivor from the solar system's earliest days, formed not from a single monolithic condensation, but from the gentle accretion of smaller bodies that never fully fused together into a solid whole. Its shape is a frozen moment, a snapshot of this fragile balance between spin and gravity that has been maintained for over 4 billion years. However, the existence of this shape raises a profound and unsettling question about its very survival. An object with such weak internal strength spinning this fast should, according to some models, be on the verge of flying apart. The centrifugal forces at its equator should theoretically exceed its gravitational binding energy. The fact that Varuna not only holds together but has maintained this configuration for eons suggests there are forces at work we don't fully understand. Perhaps a thin crust of stronger material provides a cohesive shell, or maybe the friction between the individual pieces of the rubble pile provides more stability than our current models account for. Its continued existence is a defiance of physics as we currently model it for such small worlds, making it a unique laboratory for understanding the fundamental limits of how rubble pile bodies behave under extreme stress. Yet another layer is added to Varuna's mystique when we turn our instruments toward its thermal signature, and the readings we get are anything but ordinary. This is our fifth great mystery, the temperature anomaly. In the freezing void of the Kuiper Belt, the rules of thermodynamics are seemingly straightforward. An object's surface temperature is primarily governed by its distance from the sun and its albedo, or darkness. A dark, low albedo surface should absorb more solar radiation and thus be warmer than a bright, highly reflective one that bounces most of that energy away. Given Varuna's profound darkness, one would logically predict its surface to be relatively warmer than some of its brighter, ice-covered neighbors. However, the actual data tells a much more complicated and puzzling story. Measurements of Varuna's thermal emissions reveal a surface that is significantly colder than current models predict. It's not just a slight miscalculation. It's a substantial deviation that points to a gap in our understanding of how this world functions. For a body with its known dimensions and its incredibly dark surface, the observed temperatures are bafflingly low. This creates a thermodynamic paradox. How can a surface so efficient at absorbing the sun's meager energy somehow remain so deeply frozen? It defies the simple balance between absorption and emission that governs most other bodies in the solar system. This anomaly forces us to look beyond simple explanations and consider more complex, hidden processes at work on or within this distant world. One compelling hypothesis to explain this deep chill involves the specific nature of its dark surface material. Perhaps the substance covering Varuna isn't just dark, it might possess exceptionally poor thermal conductivity. Imagine a blanket of extremely porous, fluffy dust and complex organic polymers, a cosmic powder that might be great at absorbing visible light, but is terrible at conducting that captured heat downward. In this scenario, the minuscule amount of heat from sunlight is not transferred inward. Instead, it is very efficiently re-radiated back into space as infrared energy from the very surface layer that absorbed it. The heat never gets a chance to penetrate and warm deeper layers, effectively making the surface act like a perfect cold insulator. This would be akin to how a black asphalt road gets scorching hot in the sun on Earth, while a black, porous foam block might not, because the foam traps the heat at the very surface and doesn't let it sink in. However, an even more tantalizing possibility exists, that Varuna's unexpected coldness is not just a surface phenomenon, but a clue to something happening deep within. The models that predict a warmer surface assume the object is a cold, dead rock, its internal heat from radioactive decay long since dissipated. But what if that's not true? What if Varuna possesses some latent internal heat source? This seems counterintuitive. How could internal heat make the surface colder? The answer may lie in a process called sublimation. If there is even a faint trickle of warmth coming from the interior, it could be just enough to slowly vaporize volatile ices like nitrogen, methane, or carbon monoxide that might be mixed within the subsurface. As these ices turn to gas, they would absorb immense amounts of latent heat from their immediate surroundings in a process known as endothermic cooling. This would act like a natural refrigeration unit, with the sublimating gases actively drawing heat away from the near-surface environment and effectively giving Varuna a kind of anti-heat source that chills it from within. The resulting gases might then travel through the porous, rubble pile structure until they escape into the vacuum of space, taking that stolen heat energy with them and leaving the surface even colder than if the world were simply inert. This process would create a thermal imbalance that our standard models, which treat these worlds as thermally dead, completely fail to account for. The temperature anomaly, therefore, isn't just a curiosity. It's a potential window into Varuna's active and dynamic interior, suggesting that even in the farthest, coldest reaches of our solar system, these worlds are not the static fossils we once believed them to be. Spectral analysis provides our sixth great mystery, offering a way to peer across the billions of kilometers and decipher the very ingredients that make up Varuna's dark crust. By carefully dissecting the faint sunlight reflected from its surface, astronomers can identify the chemical fingerprints of different materials. The data reveals a spectrum that is at once familiar and deeply strange, a cosmic recipe that includes expected ingredients but in baffling proportions. We see the clear signature of water ice, the bedrock of most outer solar system objects. We also detect the presence of complex, dark organic compounds, likely the very tholins that contribute to its profound darkness. Yet the ratios of these materials are all wrong, creating a compositional puzzle that sets Varuna apart from its Kuiper Belt cousins and challenges our classification of these distant worlds. The presence of water ice is confirmed, but it is not the dominant, fresh ice we see on many other trans-Neptunian objects. Instead, the spectral signature suggests it is heavily processed, perhaps buried beneath a thick mantle of darker material, or intimately mixed with it in a way that masks its reflective properties. This is a key distinction. On a world like Pluto, vast expanses of relatively pure water ice act like a bright canvas. On Varuna, the water ice seems to be a minority component, playing a secondary role to the more enigmatic dark material. This leads to a fundamental question about its formation. Did Varuna simply form in a different region of the primordial solar nebula, one that was richer in carbonaceous and organic material and poorer in water ice? Or has some unique process over billions of years selectively removed or hidden its water ice while preserving or enhancing the darker components? The nature of the dark material itself is the heart of the mystery. The spectrum is consistent with complex organics known as tholins, which are not a single compound but a class of macromolecules formed when simple ices like methane or nitrogen are zapped by radiation. However, the specific absorption features don't perfectly match the tholin spectra we've measured from other bodies like Pluto or Titan. This suggests that Varuna's tholins might have a different composition, perhaps because they were cooked from a different primordial soup of ices or under unique conditions. Another possibility is that the dark coating isn't purely tholin at all, but includes a significant amount of primordial, unprocessed carbon. This could be similar to the very dark, carbon-rich material found on certain asteroids, suggesting Varuna might share an unexpected genealogical link with much smaller, rocky bodies from the inner solar system rather than its icy Kuiper Belt neighbors. This compositional oddity could be the missing link that explains other Varunan mysteries. Its unexpected coldness, for instance, might be tied to this specific mix of materials. A surface rich in certain types of porous, complex organics could have the perfect insulating properties to create the observed thermal anomaly, preventing absorbed solar heat from penetrating the subsurface. Furthermore, the presence of specific ices, like frozen methane, could be the driver for endothermic cooling if they are sublimating due to a faint internal heat source. The bizarre composition isn't just a curiosity. it appears to be the underlying cause of the world's overall behavior, governing its temperature, its appearance, and its stability. Unlocking the precise recipe of its surface is therefore essential, as it provides the chemical context for every other process we observe, painting a picture of a world built from a uniquely ancient and mysterious set of ingredients. Moving from the chemical makeup of its surface to the subtle dance of its motion through space, we encounter our seventh great mystery, the tantalizing possibility that Varuna is not alone. Astronomers, meticulously tracking the dwarf planet's movement and rotation, have detected subtle inconsistencies, tiny gravitational tugs, and rhythmic dimmings in its light that strongly suggest the presence of an unseen companion, a moon orbiting this dark, elongated world. This is a celestial detective story built on circumstantial evidence, where the shadow of an object we have never directly seen is perhaps the most compelling clue of all, pointing to a dynamic past that may have involved a dramatic collision. The primary evidence comes from a careful analysis of Varuna's light curve, the precise measurement of its brightness over time. For a solitary, irregularly shaped object like Varuna, we expect a predictable, repeating pattern of dimming and brightening that corresponds directly to its 6-hour rotation. Its elongated shape should cause a smooth, double-peaked light curve as its larger and smaller sides turn toward Earth. However, some observations have recorded additional, smaller dips in brightness that occur outside this regular rhythm. These anomalous dimmings are exactly what we would expect if a separate, smaller body were periodically passing in front of Varuna, briefly blocking a tiny fraction of its already faint light in a series of miniature eclipses. While not yet conclusively proven, this pattern remains one of the strongest indirect arguments for a satellite. Further supporting this idea are the precise calculations of Varuna's mass. The only way to accurately determine the mass of a distant solar system object is by measuring its gravitational influence on another body. If a moon is present, the orbital characteristics of that binary system reveal the combined mass of the pair. In Varuna's case, estimates of its mass based on its assumed size and density have sometimes seemed at odds with other data. Some models suggest that to account for its rapid rotation and elongated shape without flying apart, Varuna must be more massive than its calculated size would imply if it were a single object. One elegant solution to this discrepancy is to propose that the system's mass is distributed between Varuna and an unseen moon, with a gravitational interplay between the two providing the additional stability that allows the primary world to maintain its frantic spin. The existence of a moon would immediately solve several other puzzles. The wild, eccentric orbit of Varuna itself is likely the result of a gravitational encounter with Neptune billions of years ago. Such a violent gravitational scattering event would have been tremendously disruptive, and it's statistically very difficult for a loosely bound rubble pile object to survive it without being torn apart. However, if Varuna was a binary system even before that encounter, the gravitational bond between the two bodies could have acted as a stabilizing factor, helping the pair survive the gravitational slingshot from the ice giant and remain together on their new, stretched-out path around the sun. The moon, in this scenario, is a witness and a participant in that ancient trauma. Naturally, the question of how such a moon could have formed leads to dramatic theories. The most plausible explanation is a giant impact. In the chaotic early Kuiper Belt, a catastrophic collision between a proto-Varuna and another sizable object could have ripped material from both bodies, hurling debris into orbit. Some of that debris would have later coalesced to form a moon, much as the Earth's moon is thought to have formed from a collision with a Mars-sized body. This theory is particularly attractive because it could also explain Varuna's rapid rotation. The same impact that set it spinning like a top could have also provided the raw material for a satellite. The moon would therefore be a living relic of the most violent day in Varuna's history, a permanent reminder of the impact that shaped its destiny. The frustrating and fascinating part of this mystery is our current inability to confirm it. Directly imaging a small, dark moon orbiting so close to an equally dark and distant primary world is at the very limit of our telescopic capabilities, like trying to spot a single black light bulb next to another in a pitch-black room from thousands of miles away. The Hubble Space Telescope and other powerful observatories have looked, but so far, no definitive, direct detection has been made. This leaves us in a state of suspended anticipation, with the evidence compelling but not yet conclusive. The potential satellite of Varuna remains a ghost in the data, a gravitational whisper that promises to reveal a deeper chapter in the story of this mysterious world, if only we can find a way to listen more closely. Delving deeper into the very fabric of this distant world brings us to our eighth and perhaps most fundamental mystery, the enigma of what Varuna is actually made of, or more precisely, how much it weighs for its size. Pinpointing the density of a remote object is a cornerstone of planetary science, as it reveals the balance of rock to ice within it and speaks volumes about its internal structure and formation history. For Varuna, this basic measurement has become a source of profound confusion and debate. Different scientific teams, using different observation methods and models, have arrived at wildly conflicting estimates. Some calculations suggest a density as low as 0.992 grams per cubic centimeter, a value so low it would mean Varuna is less dense than water ice itself and would literally float if placed in a vast imaginary ocean. Other, more recent analyses point toward a significantly higher density, potentially as high as 1.5 grams per cubic centimeter, which would imply a much rockier composition. This staggering discrepancy is not a minor margin of error. It represents a complete dichotomy in our understanding of this world's very nature, forcing us to choose between two radically different versions of Varuna. A density at the extreme lower end of this range would be nothing short of revolutionary. Pure water ice has a density of about 0.93 grams per cubic centimeter. For Varuna to have an average density even lower than that, its structure would have to be incredibly porous. This isn't just a simple rubble pile. It would have to be an extraordinarily fluffy and loosely packed collection of icy fragments with vast gaps and void spaces between them, more like a cosmic snowball than a compacted world. Such an object could only exist if it had never experienced any significant internal heating or compression over its 4.5 billion year lifetime, preserving a pristine, delicate architecture from the very dawn of the solar system. This version of Varuna would be a fragile relic, a time capsule of the initial gentle accretion processes that built the first planetesimals. Its incredibly low density a direct reflection of the cold and calm conditions of its birth. On the opposite end of the spectrum, a density of 1.5 grams per cubic centimeter paints a completely different picture. This value is far more typical for a mixture of rock and ice found in many other Kuiper Belt objects. It suggests a much more consolidated interior, one where the material is tightly packed with minimal porosity. This could indicate that Varuna did experience some internal heating in its past, perhaps from the decay of short-lived radioactive isotopes. This gentle warmth would have been enough to soften the ice, allowing the structure to compact under its own gravity, squeezing out the empty spaces and creating a far more solid and robust world. A Varuna with this higher density would be a much more evolved and processed body, its interior having undergone significant change since its initial formation. This discrepancy is therefore not just about numbers, it's a debate about whether Varuna is a perfectly preserved fossil or a dynamically evolved world. The primary source of this confusion stems from the immense challenge of measuring two basic properties from 4 billion miles away, size and mass. We cannot simply weigh Varuna or fly a spacecraft past it to measure its gravitational pull. Its size is estimated primarily from combining its observed brightness with a model of its surface reflectivity. If we overestimate how reflective its surface is, we will consequently overestimate its size, making it seem larger and, for a given mass, less dense. This is a critical problem with Varuna because its true albedo is one of its very mysteries. If its surface is even darker than we currently believe, then the object must be smaller than our estimates to account for its observed brightness. A smaller size with the same mass immediately leads to a much higher calculated density. The uncertainty in its darkness directly propagates into the uncertainty in its density, creating a frustrating circular problem where solving one mystery is the key to solving the other. This density puzzle is the master key that could unlock all of Varuna's other secrets. Its bizarre, elongated shape is a perfect example. If its density is confirmed to be very low, then its status as a fragile, fast-spinning rubble pile that is somehow holding itself together becomes an even more astonishing defiance of physics. The centrifugal force from its rapid rotation would pose an even greater threat to its structural integrity, making its continued existence a true marvel. Conversely, a higher density would suggest a stronger, more solid interior that could more easily withstand the forces trying to pull it apart, making its shape slightly less mysterious but its formation history more complex. The potential presence of a moon also hinges on this. A more massive Varuna, implied by a higher density for a given size, would have a stronger gravitational grip, making it easier for it to hold onto a satellite after a giant impact. Every aspect of Varuna's story, from its spin and shape to its temperature and potential companion, is filtered through the lens of this one critical and still unknown fundamental property, its true density. Until we can send a mission to this distant world or make observations with a new generation of telescopes, the essential nature of what Varuna is made of remains one of its most deeply buried secrets. This brings us to our ninth great mystery, a phenomenon that challenges our very notion of a static, frozen deep space tomb, the possibility of seasons on Varuna. At first glance, the idea seems almost laughable. This is a world so far from the sun that its light is little more than that of a brilliant star in a perpetually black sky, where temperatures hover barely above absolute zero. How could an object in such a profoundly cold and stable environment possibly experience meaningful change? Yet, careful long-term observations suggest that Varuna's surface is not entirely inert. There are subtle but detectable shifts in its brightness and spectral signature over time, hints of a slow, rhythmic cycle that points to active processes on its surface, a faint heartbeat in the cosmic dark. The primary driver of any seasonal cycle is the change in solar energy received by a world as it orbits its star. For Earth, with its nearly circular orbit and modest axial tilt, these changes are relatively gentle. For Varuna, with its wildly elliptical path, the variation is extreme. The difference in solar energy it receives at its closest approach to the Sun, or perihelion, compared to its most distant point, aphelion, is a staggering 38%. This isn't a minor fluctuation, it's a dramatic swing in the minuscule amount of warmth that reaches this distant world. As it journeys along its 280-year orbit, it experiences a slow-motion summer for a few decades as it swings past perihelion, followed by an immensely long and deepening winter as it retreats back toward the outer darkness. This orbital rhythm provides the potential engine for change, a pulse of energy that, however faint, could be enough to trigger activity on its surface. The most likely manifestation of these seasons involves the sublimation and recondensation of highly volatile ices. On a world like Varuna, water ice is as hard as rock and utterly immobile. However, ices of nitrogen, methane, or carbon monoxide have much lower freezing points and can transition directly from a solid to a gas or vice versa, even at these incredibly low temperatures, given just a tiny nudge of energy. The theory is that during Varuna's summer, When it is marginally closer to the Sun, certain areas on its surface, particularly those facing the Sun, might warm just enough to cause patches of these supervolatile ices to sublimate, turning directly into a tenuous, temporary gas. This process would darken those areas slightly as the dark underlying substrate is exposed, and perhaps even create a fleeting, localized atmosphere, a vanishingly thin exosphere of gas molecules. Then, as Varuna continues on its path and temperatures begin their long fall, the opposite occurs. Those gases, having nowhere to escape the world's weak gravity, would eventually recondense back onto the coldest parts of the surface, perhaps at the poles or on the night side, forming a new, thin, bright frost layer. This cycle of sublimation and condensation would create a slow, global exchange of material, a kind of weather system operating over centuries. The observed changes in Varuna's overall brightness and color could be the direct result of these ices migrating from one part of the surface to another, altering its reflectivity in a predictable seasonal pattern. The profound mystery, however, is how this is even possible. The energy available is almost unimaginably small. The change in temperature between its perihelion and aphelion is calculated to be only a few degrees, a shift that seems trivial against a backdrop of near-absolute cold. For such a small energy input to drive global resurfacing requires a surface that is exquisitely sensitive, almost unstable. This suggests that the volatile ices on Varuna must exist in a very pure and exposed state, poised on a knife's edge between solid and gas. It also implies that the dark material covering most of the surface must be an incredibly effective absorber of what little sunlight exists, heating up just enough to trigger the sublimation of the ices immediately beneath it. The existence of seasons on Varuna, therefore, isn't just a curiosity. It's a sensitive indicator of the precise physical and chemical state of its surface, a state we are only beginning to understand. It reveals a world that is not dead but dormant, responding to the faintest whisper of the sun with a slow, deliberate, and mysterious dance of ice and shadow. Yet the complex patterns we observe in its light curve point to something far more intricate than a simple, smooth ellipsoid. When astronomers measure its brightness with extreme precision over many rotations, they find that the light curve is not perfectly symmetrical or consistent. The peaks and troughs of brightness vary slightly in their depth and timing from one rotation to the next. These subtle anomalies are the telltale signatures of a surface that is not uniform. Instead of a homogeneous blanket of dark material, Varuna's crust appears to be a patchwork of different terrains, with some regions slightly darker or slightly brighter than others, creating a complex mosaic that reveals itself through these minuscule fluctuations in reflected light. This surface heterogeneity is the most straightforward explanation for the oddities in the light curve, but it immediately raises a deeper question. What could create such variation on a world assumed to be a static, ancient relic? One possibility is that we are witnessing the result of those incredibly slow seasonal cycles. The sublimation and redeposition of volatile ices could be creating temporary frosts in some areas, brightening them for a time while exposing the darker substrate elsewhere. This process would create a slowly shifting pattern of light and dark across the surface, a dynamic canvas that changes over decades or centuries, explaining why the light curve doesn't repeat with perfect fidelity over short observation periods. Another, more dramatic possibility is that we are seeing evidence of recent impacts. The Kuiper Belt is still an active environment, albeit at a much reduced level compared to the early solar system. A relatively recent collision with a smaller object could have excavated a fresh, bright crater of water ice from beneath the dark surface layer, creating a stark, bright spot that would significantly alter the light curve as it rotates into view. Alternatively, the impact could have scattered dark ejecta across a brighter area, creating a new dark patch. Either scenario would introduce a new feature into the rotational light curve, a blemish that wouldn't smooth out over time. Perhaps the most intriguing explanation for the complex light curve involves not just the surface but the shape itself. The prevailing model is that Varuna is a triaxial ellipsoid, a stretched-out watermelon shape. But what if its form is even more irregular? It could possess a significant equatorial bulge, or even a single large mass concentration that creates a gravitational anomaly, pulling the surface into a shape that isn't a perfect smooth curve. If Varuna is indeed a rubble pile, it's possible that its internal structure is lumpy and irregular, with denser clusters of rock buried within the matrix of ice. This would cause the overall shape to be subtly warped, not following a clean geometric formula, which would in turn create a far more complex pattern of light and shadow as it spins. The mystery of the light curve is ultimately a reminder of the limits of our remote observations. From our vantage point billions of kilometers away, Varuna is little more than a single pixel of light. The intricate details of its light curve are our only way to map its surface and infer its topography. Each tiny dip and peak is a data point in a grand puzzle, a cipher that we are still learning to decode. The unexplained variations are a siren's call to further exploration, hinting at a world of far greater complexity and activity than we ever imagined, a dynamic and patchwork world spinning in the endless night. If the profound darkness of Varuna's surface presents one thermodynamic riddle, the way it manages the minuscule amount of heat it absorbs presents another, even more baffling layer to the mystery. This is the puzzle of thermal inertia, a concept that measures how slowly or quickly a material's temperature changes in response to heating. A surface with high thermal inertia, like a rocky beach, heats up slowly in the sun and cools down slowly at night. A surface with low thermal inertia, like loose sand, changes temperature almost instantly. For a distant, cold world like Varuna, measuring this property gives us a remote sense of its surface texture and composition. Is it solid and rocky or fluffy and porous? The data we have suggests an answer that defies all straightforward expectations, pointing to a surface that behaves in a way we can't yet fully explain. The observations that reveal this puzzle come from measuring Varuna's thermal emissions at different points in its rotation. As its dark surface absorbs the feeble sunlight, it heats up slightly and re-radiates that energy back into space as infrared light. By carefully tracking these infrared emissions, astronomers can map the temperature variations across the surface. For a homogeneous object spinning every 6 hours, you would expect a predictable pattern. The afternoon side, which has been baking in the sunlight for a few hours, should be at its warmest, while the morning side, just emerging from the long night, should be at its coldest. The temperature difference between these regions should be directly related to the surface's thermal inertia. What scientists have found, however, is that these temperature variations are far smaller than predicted. The day side doesn't get as warm as it should, and the night side doesn't get as cold. The entire world seems to be thermoregulating itself, maintaining a more uniform temperature across its surface than its rapid rotation and dark color would suggest. This implies an exceptionally high thermal inertia, meaning the surface material is very good at storing heat and releasing it slowly over time. This is deeply counterintuitive. How can a world so small and so cold, presumably made of poorly conducting ices and rocks, possibly have a surface that acts like a giant thermal battery, resisting temperature change with such efficiency? One compelling theory is that Varuna's surface is not a solid slab of ice, but an incredibly porous and fluffy layer of fine dust and complex organic polymers. This might sound like it would have low thermal inertia, but the opposite can be true for a perfect insulator. Think of a thick layer of fresh snow on a sunny winter day. Even though the sun is shining, the air temperature might be below freezing, yet the snow itself doesn't immediately melt. Its complex, air-filled structure is a fantastic insulator. It absorbs solar radiation at the very surface, but the heat cannot conduct downward easily because the millions of tiny contact points between snowflakes are terrible at transferring energy. The heat becomes trapped in the topmost layer, which then re-radiates it back into space without ever warming the layers below. This creates a high effective thermal inertia because the surface temperature cannot change rapidly. The energy is either immediately reflected or re-radiated. A fluffy, powdered sugar-like surface on Varuna could explain the muted temperature swings, acting as a cosmic thermos that maintains a steady chill. An alternative and even more fascinating explanation involves hidden activity beneath the crust. What if the heat from the sun isn't just being stored, but is being actively transported away from the surface? This could happen through a process called sublimation-driven cooling. If the weak sunlight is just enough to cause tiny amounts of highly volatile ices like nitrogen or methane to turn from solid directly to gas, the process would act as a powerful cooling system. These ices would absorb vast amounts of latent heat from their immediate surroundings to make the phase change, effectively acting as a refrigeration unit. This stolen heat would then be carried by the gas as it migrates through the porous surface layer and escapes into space. This would prevent the surface from ever reaching the predicted peak temperatures, as any incoming solar energy is immediately used up in the sublimation process rather than heating the surface. The result is a world that appears to have a high thermal inertia because it is actively fighting against temperature change, not through storage, but through a constant, energy-consuming process of cooling itself down. This thermal inertia puzzle is not an isolated curiosity. It is a fundamental key to understanding Varuna's present state and its past. A fluffy, pristine surface would suggest a world that has been utterly dormant for billions of years, its exterior never compressed by impacts or geological activity. An actively sublimating surface, however, paints a picture of a dynamic world, however faintly, still processing the tiny amount of energy it receives. Unraveling which of these scenarios is correct would tell us not just what Varuna's surface feels like, but whether it is a static museum piece or a world with a subtle, ongoing heartbeat, quietly defying the absolute cold of its deep space tomb. The path of a celestial body is often a map of its history, and in the outer solar system, the most significant landmarks on that map are carved by the gravity of Neptune. Many residents of the Kuiper Belt find themselves locked in a stable, repeating gravitational dance with the ice giant, a relationship known as an orbital resonance. These resonances act as cosmic safe havens, protecting objects from destabilizing close encounters and explaining the long-term survival of populations like the Plutinos. Yet, when we examine Varuna's orbital parameters, it stubbornly refuses to fit into any of these neat, established categories, presenting a mystery of gravitational independence that challenges our models of the Kuiper Belt's architecture. An orbital resonance occurs when the orbital periods of two bodies form a simple integer ratio, like two musicians playing in a synchronized rhythm. For instance, Pluto is in a 2-to-3 resonance with Neptune. For every 2 orbits Pluto completes, Neptune makes 3. This lock ensures that whenever Pluto catches up to Neptune's orbital position, it is always at its farthest point from the giant planet, a configuration that prevents gravitational chaos over billions of years. For a large object like Varuna to exist outside such a protective relationship is unusual, suggesting a history that was either incredibly lucky or remarkably violent. It implies that Varuna has been navigating the gravitational minefield of the trans-Neptunian region without a safety net, relying on the precise geometry of its orbit alone to avoid catastrophic encounters. The search for a resonance is a precise mathematical exercise, and Varuna's numbers simply don't align. Its orbital period of approximately 280 years does not form a clear, low integer ratio with Neptune's 165-year orbit. Calculations show it might be close to an 11:6 resonance, but this is a weak, high-number ratio that doesn't provide the same stabilizing, protective effect as the stronger, simpler resonances. It's a bit like being almost in step with a marching band. The rhythm is similar, but the misstep means you're just as likely to be jostled as you are to be carried along. This puts Varuna in an ambiguous class of objects often called the non-resonant or classical population, but its significant orbital eccentricity makes it an outlier even within that group. This gravitational ambiguity points toward a dramatic origin story. The prevailing theory of the Kuiper Belt's formation, the NICE model, describes a period of planetary migration where Neptune and the other giant planets shifted their positions, scattering countless icy bodies in their wake. Many objects were captured into resonances during this migration, like driftwood being gathered by a tide. Varuna's failure to be captured suggests it might have been a late arrival to the scattering process, perhaps ejected into its current orbit after the main period of planetary migration had already concluded, missing the gravitational window for capture. Alternatively, its initial trajectory might have been so extreme that even Neptune's powerful gravity could not neatly lock it into a stable rhythm, instead leaving it on this precarious, solitary path. Being a non-resonant object with a high eccentricity has profound implications for Varuna's long-term future. Resonances provide long-term stability, effectively guaranteeing an object's orbital survival for billions of years. Without that protection, Varuna's path is inherently less predictable over astronomical timescales. Its orbit is more susceptible to gradual perturbations from Neptune's gravity, which could slowly alter its trajectory, potentially leading to a close encounter that flings it inward toward the Sun to become a centaur object, or outward into the scattered disk or even interstellar space. Its current existence is a snapshot in a much longer, unstable film, and its refusal to conform to a simple resonant pattern marks it as a transient wanderer in the outer darkness, a world on a path that is anything but guaranteed. This leads us to a mystery that is written in the absence of features, the startling lack of craters on Varuna. In the ancient, violent expanse of the Kuiper Belt, every object is a testament to bombardment, its surface a historical record written in the scars of countless impacts. We expect these distant worlds to be heavily cratered, pockmarked landscapes that have remained unchanged for billions of years, much like our own moon. Yet, the limited data we have for Varuna tells a different story. While we cannot yet resolve surface details directly, sophisticated analysis of its light curve and thermal properties suggests a surface that is unexpectedly smooth for its age, showing a glaring deficit of the large impact craters that should, by all rights, dominate its frozen crust. This absence of craters presents a profound chronological puzzle. The Kuiper Belt is the solar system's antique attic, filled with remnants from the era of planet formation. The rate of impacts was immense in the beginning and has tapered off over time, but it never truly stopped. For Varuna to have so few visible large craters, something must have been actively erasing them. This points toward a surface that is, in geological terms, surprisingly young. It implies that within the last billion years, or perhaps even more recently, some process or event has worked to renew Varuna's face, effectively giving it a cosmic facelift that wiped away the evidence of its most ancient collisions. This is a concept that forces us to completely reconsider Varuna as a static, dead world. The question, of course, is what power could possibly drive such resurfacing on a small, frozen body so far from the Sun's energy. One compelling theory points inward to the possibility of residual internal heat. Even a small, rocky core contains radioactive elements like potassium, uranium, and thorium. As these elements decay, they generate a faint, steady trickle of warmth. In a large, insulated world, this heat can build up over billions of years. If Varuna's interior is just porous enough to act as a good insulator, This radiogenic heat might have been sufficient to slowly soften and melt the deepest layers of its icy mantle. This could have allowed for a sluggish form of solid-state convection, where warmer ice slowly rises from the interior, pushing against and smoothing out the crust above in a process called cryovolcanism. This wouldn't be volcanic eruptions of lava, but rather a slow oozing of a warm, slushy ice mixture that floods and fills in topographical lows, effectively erasing craters under a new blank layer. Another fascinating possibility involves the seasonal sublimation and condensation cycles we discussed earlier, but on a much grander scale. If Varuna's orbit and axial tilt create significant enough temperature variations, they could drive a powerful, slow-motion weather system. Volatile ices like nitrogen or methane could sublimate from the warmer equatorial regions and migrate to condense as permanent frost at the much colder poles. Over millions of years, this continuous transfer of material could literally sand down topographic features, burying craters under thick deposits of bright frost and creating vast, smooth plains at the poles, while simultaneously excavating older terrain at the equator. This process would constantly refresh the surface, creating a world whose appearance is shaped not by impacts, but by an ongoing atmospheric dance. There exists an even more dramatic one-time event scenario, a catastrophic impact. It's possible that Varuna was struck by another sizable Kuiper Belt object relatively recently in geological terms. The energy from such a colossal collision would have been immense, generating enough heat to melt a significant portion of its icy crust. The entire surface could have been temporarily liquefied, sloshing like water in a bucket before refreezing into a perfectly smooth, glassy plain, wiping the geological slate completely clean. The same impact that gave Varuna its rapid spin could also be responsible for its smooth appearance, a single transformative event that reshaped its destiny in multiple ways. Each of these theories has its own compelling evidence and significant challenges, leaving the mystery of Varuna's missing craters wide open, a quiet enigma on a dark world that speaks volumes about the hidden forces still at work in the farthest reaches of our solar system. But the subtle clues we gather from its light are not limited to brightness alone. They extend into the very color of this distant world, presenting our 14th great mystery. When astronomers break down the faint sunlight reflected from Varuna into its constituent colors, they don't find a uniform shade of deep space black. Instead, they detect subtle variations, a patchwork of very slight color differences across its surface, with some regions exhibiting a noticeably redder hue than others. This isn't the stark contrast of a red pole and a black equator, but rather a delicate gradient, a whisper of spectral diversity that hints at a surface far more complex and active than a simple, homogeneous blanket of ancient dust. The presence of these color variations is a direct challenge to the idea of Varuna as a static, inert fossil. A world that has been completely dormant for billions of years would be expected to have a uniform appearance. The constant rain of cosmic rays and micrometeorite dust would have space weathered the entire surface equally, creating a single, consistent layer of dark gunk. The fact that we see color differences means that some process must be actively disturbing this uniformity, either by exposing fresh material from below or by depositing new material on top in a localized way. It's a sign that Varuna's surface is a dynamic canvas, albeit one that changes at a glacial pace. The leading explanation for the reddish patches points directly to the complex organic compounds known as tholins. As we've discussed, these reddish-black substances are created when simple ices like methane are irradiated over long periods. The puzzle, however, is why this process isn't uniform. Why are some areas redder than others? One possibility is that we are seeing different thicknesses of this tholin layer. Areas where the dark coating is thickest would appear the darkest and potentially the reddest, as the complex polymers have had the most time to develop. In contrast, slightly brighter, less red areas might be places where this dark blanket is thinner, allowing the slightly less red coloration of the water ice bedrock underneath to subtly influence the overall color. Another compelling theory involves the slow migration of volatile ices. Imagine that a patch of pure methane ice becomes exposed on the surface, perhaps from a tiny impact or a crack caused by Varuna's rapid spin stressing its structure. This fresh, bright white ice would initially make that area appear less red. But then, over centuries, the relentless barrage of cosmic radiation would begin to work on that exposed methane, slowly polymerizing it into a new layer of reddish tholins. What we might be witnessing in the color variations is a snapshot of this incredibly slow process, different patches of surface at different stages of this chemical evolution. Some areas are fresh and still turning red, while others are ancient and have reached their final, dark red terminus. The variations could also be driven by Varuna's extreme seasons and its elliptical orbit. When it is closer to the Sun during its perihelion, certain latitudes might receive just enough extra energy to trigger more vigorous sublimation of the most volatile ices. This would leave behind a higher concentration of the less volatile, redder tholins in those sunnier regions, effectively enhancing their redness. Then, as it moves away, ices might recondense more heavily in the colder polar areas, creating temporary bright, less red frosts that mask the darker substrate below. The color map of Varuna could therefore be a slowly shifting chart of its temperature variations, a direct reflection of its orbital journey. Unraveling the precise meaning of these color variations is like trying to read a history book in a foreign language where we only know a few words. Each slight shift in hue is a sentence describing the composition, age, and activity of a tiny patch of this distant world. The redder areas tell a story of long exposure and complex chemistry, while the less red areas speak of recent change and renewal. Together, they paint a picture of a world that is not dead but slowly breathing, its surface engaged in a perpetual, silent dance between radiation, chemistry, and the faint, cold whisper of a distant sun. Beyond its physical characteristics lies a more poetic layer of its identity, its very name. Our 15th mystery delves into the origin of Varuna and the profound mythological connection it implies. In the early 2000s, as astronomers began discovering a host of new worlds in the Kuiper Belt, they faced the challenge of bestowing names that carried weight and meaning. This particular object, initially known by the impersonal designation 2000WR106, was given a name that resonates with ancient power, Varuna, drawn from the pantheon of Hindu deities. This was not a random choice from a list, it was a deliberate selection that ties this distant, icy world to the most primordial of cosmic forces. In Hindu mythology, Varuna is a supreme god of a previous age, a sovereign ruler associated with the sky, the night, the celestial ocean, and most importantly, the waters, both on Earth and in the cosmos. He is the keeper of cosmic order, known as Rita, and the divine witness to all things, often depicted as riding a mythical sea creature. The decision to name this distant body after a god of waters and the cosmic ocean is strikingly apt, yet it also feels almost prescient. When the name was chosen, very little was known about this world beyond its orbit and approximate size. Yet, as our understanding has deepened, the connection has become increasingly evocative. Could this mythological link hint at a deeper truth about its nature that the namers intuitively grasped? Consider the attributes of the deity. As the god of the cosmic ocean, his namesake now resides in the darkest, deepest ocean of our solar system, the frigid, endless sea of space within the Kuiper Belt. His association with the night sky is perfectly embodied by an object that dwells in perpetual twilight. His role as a divine witness to truth and cosmic order mirrors the scientific hope for Varuna the world, that it holds and preserves the true, unaltered record of the solar system's formation, acting as a silent witness to the events that shaped our cosmic neighborhood. The name transforms from a simple label into a narrative, framing this distant world not just as a rock, but as a celestial entity with a story to tell. This leads to a fascinating, almost metaphysical question. Does the name subconsciously shape our scientific inquiry? Knowing that Varuna is named for a god of waters, are we more inclined to search for evidence of exotic ices, cryovolcanism, or subsurface oceans? The power of a name can set an expectation, and in the case of Varuna, those expectations are tantalizing. The deity is linked to the hidden depths of the ocean, which in modern planetary science translates to the search for subsurface oceans within icy worlds. While Varuna is likely too small to host a liquid ocean like those suspected on moons like Europa or Enceladus, the mythological connection to hidden waters keeps the door open to the possibility of a slushy, briny layer deep within its interior, a remnant of its ancient formation. Furthermore, the god Varuna is often described as having 1,000 eyes, seeing all that occurs in his domain. In a scientific context, this feels like a powerful metaphor for our own efforts to study this world. We point our telescopes, our 1,000 electronic eyes, toward it, trying to glean its secrets from the faintest whispers of light. The mythology creates a framework that elevates the scientific pursuit from mere day to collection to a form of cosmic discovery, a quest to understand a world named for a watcher by becoming watchers ourselves. The name, therefore, is not just a convenient tag, it is the first piece of cultural interpretation applied to the world, a lens through which we begin to understand its place not only in our solar system but in our human imagination. It binds the cold, hard data of astronomy to the rich, symbolic language of myth, reminding us that our exploration of the cosmos is, and has always been, a deeply human story. While its rapid spin and elongated shape create a predictable rhythm of light and shadow, Varuna holds another, far more erratic secret in its pattern of brightness. This 16th mystery centers on the truly unexpected variations in its luminosity, fluctuations that occur outside the regular cadence of its 6-hour rotation or the slow, centuries-long pulse of its orbital seasons. These are not the subtle, gradated shifts we might expect from a slowly changing world, but rather pronounced and irregular changes in brightness that have been recorded over years of observation. These anomalies suggest moments where Varuna, for reasons we cannot yet explain, suddenly shines a little brighter or dims a little more profoundly against the backdrop of space, hinting at sudden, explosive events on its surface. The challenge for astronomers is to rule out all mundane explanations for these flickers. Could it be an observational artifact, a trick of the Earth's atmosphere, or the sensitivity of our telescopes? Meticulous analysis suggests the changes are real and intrinsic to the object itself. Perhaps it's caused by a particularly large and dark storm in our own atmosphere, momentarily dimming its light. The patterns don't align with local weather data. Maybe it's the result of passing through a faint, unseen cloud of interstellar dust. The changes are too frequent and too specific to Varuna to support that. Having ruled out these external factors, we are left with the startling conclusion that the source of these variations must be on Varuna's surface or in its immediate environment, pointing to a level of sporadic activity we never anticipated from such a distant and frozen body. The most tantalizing explanation for these sudden brightening events is the possibility of outbursts, similar to those observed on comets when they approach the sun. On a comet, heat from the sun vaporizes subsurface ices, building pressure until the gas bursts through a weak spot in the crust, jetting into space and carrying with it a cloud of bright, reflective dust particles. This process temporarily surrounds the comet in a brilliant halo, dramatically increasing its brightness. For this to happen on Varuna, a world over 40 times farther from the sun than Earth, requires a radical rethinking of its internal energy. The feeble sunlight at that distance provides nowhere near enough heat for such violent sublimation. This implies that the energy source for any potential outburst must come from within Varuna itself. This leads us to a profound hypothesis that Varuna may harbor pockets of volatile ices trapped under pressure beneath its dark, insulating crust. Over immense timescales, the faint but constant trickle of heat from radioactive decay in its rocky core could very slowly warm these volatile deposits. Trapped and unable to escape, the pressure would gradually build until it finds a release valve, a crack caused by the immense mechanical stress of its rapid rotation, a tiny impact from a pebble-sized meteoroid, or simply the weakness of the overlying material. The resulting release would not be a fiery explosion, but a cold, violent jet of nitrogen, methane, or carbon monoxide gas, ripping a hole in the surface and blasting a plume of bright, fresh ice crystals high above the dark terrain. This freshly exposed ice would be far more reflective than the surrounding dark tholins, causing the entire world to appear to briefly flare in brightness as the plume expands and then slowly settles back down, dusting the area around the vent with new frost. An alternative, and perhaps even more exotic, theory involves the concept of seasonal pressure buildup on a grand scale. As Varuna journeys along its elliptical orbit, the subsurface temperature would fluctuate slightly, potentially causing vast global reservoirs of volatile ices to slowly sublimate and recondense. During its closer approach to the Sun, sublimation might dominate, increasing the pressure within its porous interior. This pressure might not release gradually, but could instead build to a critical point until it catastrophically vents from a single area, like a geyser finally erupting after a long period of underground accumulation. This would make Varuna's outbursts not random, but tied to its orbital position, a kind of scheduled yet still violent exhalation that occurs once every 280 years. The irregular dimming events present their own separate puzzle. If sudden brightening is caused by exposing fresh ice, then sudden darkening could be the result of a fresh impact. A collision with even a small object could excavate a crater, throwing up a plume of dark, subsurface material and ejecta that rains down over a large area, temporarily creating a new, larger patch of low albedo terrain that would dim the overall reflectivity of the world as it rotates. Or it could be evidence of a massive landslide on its elongated slopes, triggered by the relentless centrifugal force of its spin, which causes a section of a darker, unstable cliff face to collapse and slide, exposing a fresher but equally dark layer beneath and altering the surface albedo in a way we perceive as a dip in brightness. These irregular variations, both up and down, paint a picture of a world that is not peacefully slumbering, but occasionally stirring, its surface still being actively shaped by both internal whispers and external blows, a dynamic process that continues to unfold in the profound silence of the Kuiper Belt. This brings us to a particularly volatile ingredient in Varuna's mysterious surface recipe, methane ice. Detecting the spectral signature of methane on a distant Kuiper Belt object is not, in itself, extraordinary. It's a common component out in the freezing dark. The mystery of Varuna's methane lies in its apparent behavior and distribution. Given this world's immense distance from the Sun and its consequently feeble energy input, methane should be one of the most stable and immobile ices on its surface, frozen as solid as granite. Yet the data suggests a far more dynamic and puzzling situation, with the methane appearing in patterns and concentrations that defy this simple expectation, hinting at a complex and ongoing chemical drama. The core of the puzzle is stability. At the temperatures prevailing on Varuna, which hover around a devastatingly cold -230 degrees Celsius, methane ice is profoundly stable. It should just sit there, frozen for eons, behaving like any other inert rock. It lacks the volatility of nitrogen or carbon monoxide, which can still sublimate at those extremes. Therefore, if Varuna's surface were a simple, static blanket, we would expect any methane present to be uniformly distributed, its spectral signature appearing with consistent strength across the entire surface. However, that's not what the observations indicate. the signature of methane seems to vary, suggesting that some regions of Varuna are richer in this ice than others, a heterogeneity that shouldn't exist on a perfectly cold, dead world. This uneven distribution points directly to some form of active process that is moving methane around. One compelling explanation involves Varuna's extreme seasons. As it travels along its elliptical orbit, the amount of solar energy it receives fluctuates by over a third. While this change is minuscule in absolute terms, it might be just enough to make a difference for a substance on the thermodynamic knife's edge. During its closest approach to the Sun, certain areas, particularly those facing the Sun, might warm by a critical degree or two. This tiny nudge of energy could be sufficient to cause the very topmost layer of methane ice to sublimate, not in a violent outburst, but in a slow, deliberate vaporization. This methane gas, once free, wouldn't simply vanish into space due to Varuna's weak but present gravity. Instead, it would form a transient, incredibly thin atmosphere. This is where the magic happens. This temporary atmosphere doesn't last long. As the gas molecules travel across the surface, they would eventually encounter regions that are colder, the perpetual shadows at the poles or the night side. There, they would lose their minimal energy and recondense directly back onto the surface as a fresh layer of bright, new methane frost. This process would create a slow-motion weather system, effectively harvesting methane from the warmer equatorial regions and depositing it as a bright frost in the colder zones. Over millennia, this could create a stark contrast: dark, methane-depleted equatorial belts and brighter, methane-rich polar caps. The spectral variations we detect could be a snapshot of this ongoing redistribution, a direct reflection of Varuna's orbital position and the current state of its global methane cycle. However, an even more intriguing possibility exists, that the methane isn't just moving on the surface, but is being actively created there. This theory involves the very tholins that give Varuna its dark color. Tholins are complex organic polymers, and they are formed when simpler hydrocarbons like methane are irradiated. The process is thought to be a one-way street. Radiation breaks down methane and reassembles it into darker, more complex gunk. But what if the process can, under certain conditions, work in reverse? Could Varuna's surface chemistry be somehow regenerating fresh methane ice from these complex polymers? While highly speculative, some laboratory experiments suggest that under the influence of certain types of radiation or even cosmic rays, the breakdown of even more complex tholins could potentially release small amounts of methane as a byproduct. This would mean Varuna's surface isn't just losing methane. It could be part of a complex chemical cycle where it is both consumed to make tholins and produced from their breakdown, a self-sustaining atmospheric engine that operates on a trickle of energy. The presence and behavior of methane also provide a crucial clue to Varuna's internal composition. Methane is a volatile that is often associated with a very specific formation history. Its presence in significant quantities suggests that Varuna accreted from material that formed in a region of the primordial solar nebula that was cold enough and rich enough in carbon to allow methane to condense directly onto dust grains. This sets it apart from objects that formed closer in, which would be richer in water ice but poorer in these supervolatiles. The fact that the methane is still there and still dynamic implies that Varuna has never undergone a significant warming event that would have caused it to lose all of these volatile ices to space. It has managed to retain these primordial ingredients, making it a priceless sample of the conditions in the outer solar nebula over 4 billion years ago. The strange patterns of its methane ice are therefore not just a curiosity. They are the visible fingerprints of Varuna's ancient origin and the subtle, powerful forces that continue to shape its surface today. Yet for all its unique and defining characteristics, Varuna cannot be understood in isolation. Its true story is written in its relationship to the broader family of Kuiper Belt objects. This 18th mystery isn't about what Varuna is, but where it belongs. As astronomers have catalogued the diverse inhabitants of this distant region, they have created categories to bring order to the chaos: cold classicals, hot classicals, scattered disk objects, and resonant populations like the Plutinos. Yet, when we try to slot Varuna into one of these neatly defined boxes, we find it resists classification, a celestial rebel that defies our attempts to categorize it, and in doing so, reveals the limitations of our own taxonomic systems. Its orbit alone places it in a state of cosmic ambiguity. Objects in the Kuiper Belt are often defined by their relationship with Neptune. The cold classicals inhabit serene, circular orbits far from the ice giant's gravitational influence, pristine relics thought to have formed in place. Varuna's wildly elliptical path immediately disqualifies it from this group. The hot classicals and scattered disk objects have eccentric orbits like Varuna's, but these are typically attributed to past gravitational scattering by Neptune. While this is a likely history for Varuna, its specific orbital parameters, its perihelion distance, its inclination, its precise eccentricity, don't align perfectly with the core populations of these groups either. It sits in a fuzzy borderland, an orbital loner that shares characteristics with several families but doesn't fully commit to anyone. This classification crisis deepens when we consider its physical properties. Its profound darkness and suspected composition of rock and complex organics are reminiscent of some smaller, darker Kuiper Belt objects and even certain types of asteroids. However, its size and likely rubble pile structure place it in the realm of larger protoplanets like Haumea or Quaoar, yet it lacks Haumea's brilliant water ice surface and unique elongated shape or Quaoar's suspected ring system. It doesn't fit the mold of a volatile, rich world like Pluto or Eris, nor does it match the profile of a pure, rocky relic. Varuna seems to occupy a strange middle ground, a transitional object that embodies characteristics from multiple classes, suggesting that the boundaries between our categories are far more porous and blurred than our clean diagrams imply. This taxonomic turmoil forces a profound and exciting question. Is Varuna an oddball, a singular anomaly that formed under exceptionally rare circumstances? Or is it a perfectly standard representative of a class of objects we simply haven't recognized yet? The latter possibility is particularly thrilling. Our census of the Kuiper Belt is still incredibly young and heavily biased toward discovering the largest and the brightest objects. It is entirely possible that Varuna is not a misfit at all, but rather the first well-studied example of a major, yet previously hidden, population of dark, fast-spinning, elongated worlds. Its peculiarities might not be anomalies, but the standard blueprint for a whole family of Kuiper Belt objects that have, until now, remained too faint and too difficult to study in detail. This reframes Varuna from a puzzle to be solved into a key for unlocking a deeper understanding of the Kuiper Belt's true diversity. Its inability to be easily classified isn't a failure of observation, it's a success. It demonstrates that the outer solar system is not simply divided into a few neat categories, but is a continuum of worlds, each with its own unique history of formation, collision, and orbital migration. Varuna's blended characteristics could be the result of a blended origin. Perhaps it formed in one region of the primordial disk and was then gravitationally kicked into another, acquiring physical properties from its birthplace and orbital properties from its later scattering. It becomes a cosmic Rosetta Stone, a single object that holds clues to multiple different chapters of our solar system's violent and dynamic history, reminding us that nature delights in complexity and refuses to be constrained by the simple labels we create. This brings us to a mystery that emanates from the very core of the world, a faint whisper of heat that challenges our understanding of what powers the most remote objects in our solar system. While the sun's influence at Varuna's distance is negligible, the interior of any rocky body is warmed by the slow, steady decay of radioactive elements locked within its rock. For most small Kuiper Belt objects, this radiogenic heating is a faint trickle, long since dissipated into the void over billions of years. However, when we try to model Varuna's thermal behavior, especially its unexpected coldness and potential for surface refreshment, the numbers only make sense if we propose an internal heat source slightly stronger than expected. This points toward a startling possibility that Varuna might possess an unusually enriched concentration of radioactive elements like potassium, uranium, and thorium, a geochemical anomaly that would rewrite the story of its birth. The evidence for this is entirely indirect, a conclusion drawn from trying to balance a complex thermodynamic equation. To explain the potential for even limited cryovolcanic resurfacing or the deep-seated cooling from volatile sublimation, there must be a source of energy keeping the interior from being completely frozen solid. The feeble sunlight certainly can't do it. The residual heat from its formation should have bled away eons ago. The only remaining candidate is the energy released by radioactive decay. For Varuna to have any measurable internal warmth today, the proportion of these heat-producing elements within its rocky component must be higher than the average for the solar system. This isn't a small adjustment. It implies that the material which came together to form Varuna was peculiarly rich in these specific heavy elements. This immediately presents a profound planetary science puzzle. Radioactive elements are forged in the cataclysmic deaths of massive stars and scattered through the galaxy by supernova explosions. When our solar system formed from a collapsing cloud of gas and dust, these elements were not distributed evenly. Generally, the thinking has been that the inner solar system, where the sun's heat vaporized volatile ices, became enriched in heavier, refractory materials like rocks and metals, including radioisotopes. The outer solar system, by contrast, is thought to be dominated by lighter, volatile ices with a more diluted mixture of rocky material. Varuna, forming in the cold outer reaches, should theoretically be made from a more primitive, less processed blend of ingredients that is poorer in these dense radioactive elements. The suggestion that it might be enriched turns this expectation on its head. How could a world in the Kuiper Belt end up with such a peculiar composition? One compelling theory involves the turbulent early history of our solar system. During the first 100 million years, the giant planets are believed to have migrated outward, their immense gravity scattering countless icy planetesimals in every direction. It's possible that Varuna did not originate in the classical Kuiper Belt at all. Instead, it might have formed much closer to the Sun, in the region between the orbits of the gas giants, where the building blocks were richer in rocky and radioactive material. A gravitational kick from Jupiter or Saturn could have then hurled it outward on a trajectory that eventually settled into its current eccentric orbit, making it an immigrant in the realm of ice. Its unusual radioactivity would therefore be a lingering fingerprint of a warmer, more chemically processed birthplace, a secret history carried in its core. An alternative and even more fascinating idea is that this enrichment is a local phenomenon. Perhaps the primordial cloud that coalesced into Varuna was somehow seeded with a disproportionate amount of material from a particular supernova whose ejecta was especially rich in these specific isotopes. This would make Varuna a time capsule, preserving a unique chemical signature from a specific stellar event that occurred just before our solar system's birth. Its radioactive warmth would be the dying ember of a long-dead star, a cosmic inheritance that has been keeping this small world subtly active for over 4 billion years. Whether through dynamical scattering or a unique accretion history, the radioactivity puzzle transforms Varuna from a simple ball of ice and rock into an object with a deeply nuanced and personal geochemical story, one that continues to influence its geology and evolution to this very day. Yet another layer of intrigue surrounds the potential for Varuna to briefly cloak itself in a vanishingly thin shroud of gas, a phenomenon that defies the odds given its weak gravity and the profound cold. While it lacks the permanent atmosphere of a larger world like Pluto, there is compelling speculation that Varuna could experience short-lived, localized outbursts of atmospheric activity, triggered by the subtle interplay of its unique orbit, rapid rotation, and mysterious internal warmth. The most likely candidate for these fleeting events is the sublimation of nitrogen ice, a process that requires more energy than methane but would create a more substantial and detectable temporary atmosphere. During its closest approach to the Sun, certain dark, sun-facing patches on its surface might absorb just enough energy to cause tiny pockets of surface nitrogen to transition directly from solid to gas. This wouldn't be a global phenomenon, but rather a temporary, spotty exhalation, a whisper of gas that lingers for a brief period before either escaping to space or recondensing on the colder night side. The mechanics of such an event are incredibly delicate. For nitrogen to sublimate at all at Varuna's average temperatures, the surface material must be an almost perfect absorber of solar energy, heating up significantly despite the surrounding cold. The dark tholins covering its surface are perfect for this role. Furthermore, the gas produced wouldn't behave like a traditional atmosphere. Varuna's rapid rotation and weak gravity mean this tenuous gas wouldn't form a uniform envelope. Instead, it would likely be a collection of localized, collimated jets, similar to a comet's coma but far more faint. These jets could even contribute to Varuna's puzzling thermal inertia, as the process of sublimation itself would actively cool the immediate area, creating a self-limiting feedback loop that prevents the event from escalating out of control. The most tantalizing evidence for this activity would be a specific, hard-to-catch signature, a subtle but sudden change in the object's infrared emissions or a minute shift in its albedo as fresh frost is deposited elsewhere. Observing such a transient event is a monumental challenge requiring luck and prolonged monitoring, but its potential discovery would revolutionize our understanding of activity in the outer solar system. It would prove that atmospheric processes are not the sole domain of large planets and moons, but can occur on even small, remote worlds, driven by a precise and delicate balance of chemistry, orbital mechanics, and internal heat. These possible atmospheric whispers, though faint, suggest a world that is not entirely dead, but occasionally stirs from its icy slumber, reminding us that even in the deepest freeze, the solar system still holds a capacity for surprise. The ghost of a companion haunts our observations of Varuna, a gravitational whisper that has sparked one of the most persistent debates in its study. Is this dark, elongated world actually part of a binary system? The evidence is not in a direct image, but in the subtle, telltale wobbles and rhythmic anomalies that suggest the gravitational pull of an unseen partner. This mystery hinges on the delicate dance of two bodies bound by gravity, a celestial tango we can infer from its effects but have yet to see with our own eyes, making the question of Varuna's solitude one of its most compelling and unresolved puzzles. The primary clue comes from meticulous analysis of its light curve, the precise measurement of its brightness over time. For a solitary, irregularly shaped object like Varuna, spinning on its axis every 6 hours, we expect a predictable, repeating pattern of dimming and brightening. Yet, some datasets reveal additional, smaller dips in luminosity that occur outside this regular rhythm. These brief, anomalous dimmings are precisely what astronomers would expect if a smaller, unseen body were periodically passing in front of Varuna, briefly blocking a tiny fraction of its already faint light in a series of miniature eclipses. It's a compelling, albeit circumstantial, argument for a satellite, a shadow within the data pointing to a physical presence. Further supporting this theory are the complex calculations surrounding Varuna's mass and stability. Determining the mass of a distant object is typically done by observing its gravitational influence on another body. If a moon is present, the orbital characteristics of that binary system reveal the combined mass of the pair. Some models suggest that for Varuna to maintain its incredibly fast spin and highly elongated shape without flying apart, it must possess more mass than its estimated size would imply for a solitary object. The most elegant solution to this discrepancy is to propose that the system's total mass is distributed between Varuna and a potential moon, with a gravitational interplay between the two providing the additional stability that allows the primary world to maintain its precarious configuration. The potential existence of a moon also offers an elegant explanation for Varuna's dramatic history. Its wild, eccentric orbit is likely the result of a violent gravitational encounter with Neptune billions of years ago. For a loosely bound rubble pile object to survive such a disruptive scattering event without being torn apart is statistically difficult. However, if Varuna was a binary system before that encounter, the gravitational bond between the two bodies could have acted as a stabilizing anchor, helping the pair survive the gravitational slingshot from the ice giant and remain together on their new, stretched-out path around the sun. In this scenario, the moon is not just a companion, it is a co-survivor, a silent witness to the most traumatic event in Varuna's past. Naturally, the question of how such a moon could have formed leads to dramatic theories, with a giant impact being the most plausible. A catastrophic collision between a proto-Varuna and another sizable object in the chaotic early Kuiper Belt could have ripped material from both bodies, hurling debris into orbit. Some of that debris would have later coalesced to form a moon, much as the Earth's moon is thought to have formed. This theory is particularly attractive because it could also explain Varuna's rapid rotation. The same colossal impact that set it spinning like a top could have also provided the raw material for a satellite. The moon would therefore be a living relic of the most violent day in Varuna's history, a permanent testament to the impact that shaped its very existence. The profound frustration of this mystery lies in our current technological inability to provide a definitive confirmation. Directly imaging a small, dark moon orbiting incredibly close to an equally dark and distant primary world is at the very limit of our most powerful telescopes. It is like trying to spot a single black marble next to another in a pitch-black room from thousands of miles away. The Hubble Space Telescope and ground-based observatories equipped with advanced adaptive optics have trained their sights on Varuna, but so far no conclusive direct detection has been made. The companion remains a ghost in the data, a gravitational suggestion that continues to tantalize astronomers and fuel the debate, reminding us that some of the universe's most profound secrets are still just beyond the edge of our vision. This brings us to a characteristic that defines a world's very relationship with the cosmos around it, its axial tilt. For our 22nd mystery, we venture into the puzzling orientation of Varuna in space. While most planets and large dwarf planets have axial tilts that are either minimal, like Mercury, or moderately pronounced, like Earth and Mars, the limited data we have for Varuna suggests its axis of rotation is tipped at a significant and unusual angle. This isn't just a random piece of trivia. The tilt of a world is a fossilized record of its most violent past, a clue etched in its spin that points directly to the colossal collisions that may have shaped its destiny. Determining the axial tilt of a distant point of light is a feat of astronomical deduction. It involves meticulously analyzing the object's light curve over many rotations and across different points in its orbit. The precise pattern of brightening and dimming, the amplitude of the changes, and how these patterns shift over time all contain subtle information about the angle between its rotation axis and its orbital plane. For Varuna, this analysis is exceptionally challenging due to its great distance and dark surface, but the emerging picture points toward a tilt that is both extreme and oddly oriented, setting it apart from many of its Kuiper Belt neighbors. This unusual configuration immediately raises the question of what kind of event could have knocked a world so decisively off kilter. The most likely culprit for such a dramatic axial reorientation is once again a giant impact. In the chaotic early solar system, a collision with another sizable protoplanet wouldn't just have the power to change Varuna's orbit or spin rate. A sufficiently glancing, powerful blow could have literally tipped the entire world over, permanently altering the orientation of its rotation pole. The fact that this tilt has persisted for billions of years tells us that the impact must have been a defining moment in its history, an event so massive that it set Varuna's fundamental orientation in space for all time. This isn't a small nudge, it's a cosmic push that changed everything. The specific angle of the tilt could even hold clues about the impactor itself. Computer models of giant impacts show that the resulting axial tilt of the larger body is influenced by the angle of impact, the relative size of the impactor, and the speed of the collision. Varuna's particular tilt might therefore be the key to reverse engineering the properties of the object that struck it, allowing us to estimate its mass and the trajectory it was on. This transforms the axial tilt from a simple measurement into a window onto a specific moment in time, a digital fingerprint of a cataclysm that occurred over 4 billion years ago. Furthermore, an extreme axial tilt has profound consequences for the world's climate and geology, even in the deep freeze of the Kuiper Belt. On a world with a tilt like Earth, seasons are moderate. On a world like Varuna with a severe tilt, the seasonal contrasts would be incredibly dramatic. One pole would be pointed toward the distant sun for a significant portion of its 280-year orbit, experiencing a long, continuous summer where volatile ices might actively sublimate, while the opposite pole would be plunged into an equally long, profound winter of absolute cold, acting as a cold trap where those same volatiles would freeze out into thick deposits. This could create a planetary scale pump, driving the migration of ices from one hemisphere to the other over millennia, and contributing significantly to the surface renewal and the puzzling lack of craters. The unusual tilt isn't just a historical artifact, it may be the active engine powering Varuna's slow-motion geological activity, making it a dynamic world in a way we are only beginning to appreciate. Now we come to a profound contradiction at the very heart of understanding this distant world, a puzzle that pits its ancient origin against its potentially youthful appearance. On one hand, Varuna is a denizen of the Kuiper Belt, a region considered the solar system's most pristine antique shop, where objects are expected to be heavily cratered fossils from the dawn of planetary formation. The profound darkness of its surface, coated in complex organics called tholins, strongly suggests an incredibly ancient face. These dark compounds are not created overnight. They are the product of billions of years of relentless bombardment by cosmic rays and solar wind, slowly processing simple ices into a dark, reddish tar. This space weathering process is a clock, and Varuna's deep black hue implies its surface has been ticking for eons, exposed to the harshness of space without significant change. If this were the whole story, we would expect a landscape more cratered than our moon, a static testament to 4.5 billion years of impacts. Yet, other lines of evidence whisper a very different story, one of a dynamic and surprisingly youthful world. The most compelling clue is the startling lack of large, obvious craters. Analysis of its light curve and thermal properties, while unable to resolve surface details directly, suggests a topography that is smoother than it should be. For an object of its size and location, the expected bombardment history would have left a surface densely pockmarked. Their absence implies that something has been actively erasing these scars, effectively renewing the surface and wiping the geological slate clean within the last billion years, or perhaps even more recently. This creates a direct paradox. How can a surface be both ancient in its chemistry and young in its topography? It's as if we discovered a person with the wrinkled, weathered skin of a centenarian but the smooth, unblemished bones of a youth. One elegant solution to this paradox lies in the concept of a two-tiered surface. Imagine Varuna's crust not as a single layer, but as a complex structure. The deep, dark red color could be caused by a thin, global blanket of ancient tholins, a patina of extreme age that coats everything. However, beneath this dark veneer, the actual topography of the world, its hills, valleys, and plains, could be much younger. Geological processes could be constantly reshaping the ground, smoothing out craters and creating new plains. But this fresh terrain is immediately and continuously being recoated by that same dark tholin dust. In this model, the surface is both old and new simultaneously. The paint is ancient, but the canvas underneath is constantly being refreshed. The dark coating is continually replenished as well, as new volatile ices exposed by the geological activity are themselves irradiated and darkened, maintaining the perpetual paradox. The mechanisms for this renewal are as fascinating as the paradox itself. The leading candidate is the slow, global migration of volatile ices driven by Varuna's extreme elliptical orbit and potential axial tilt. As it swings closer to the Sun during its perihelion, certain regions may warm just enough to trigger the sublimation of highly volatile ices like nitrogen or methane. This gas then migrates across the surface until it reaches the coldest areas, the poles or the permanent night side, where it recondenses as a bright new frost. Over millions of years, this process could act like a planetary-scale plasterer, slowly filling in topographical lows and craters under meters of fresh, bright ice, which then quickly darkens. This would create a surface that is continuously being turned over, its physical features young, but its superficial color perpetually old. An alternative, more violent explanation involves cryovolcanism. If Varuna retains a trickle of internal heat from radioactive decay, it could fuel a sluggish form of geological activity. Warm, slushy ice, a mixture of water, ammonia, and other antifreeze compounds, could slowly well up from the interior and ooze across the surface in slow-motion eruptions. This cryolava would flood older terrain, burying craters and creating vast, smooth plains. When this fresh slurry of ice first reaches the surface, it will be bright and reflective. But it wouldn't stay that way for long. In the harsh environment of space, it would quickly be bombarded by radiation and darken into the same tholin layer that covers the rest of the planet. This process would create a cycle of renewal and darkening, where the surface's youth is fleeting and constantly being hidden under a mask of apparent antiquity. This paradox forces us to see Varuna not as a simple, static world, but as a complex body with a split personality, its true age hidden beneath a dark cloak that both reveals and conceals its turbulent history. Now we arrive at a mystery that radiates from the very surface of this dark world, a thermal signature that stubbornly refuses to behave as our models predict. When astronomers point their most sensitive infrared telescopes toward Varuna, they are not just measuring its dim glow, they are taking its temperature from across the solar system. The readings they get are deeply puzzling. Based on its profound darkness and immense distance from the Sun, we would expect its surface to absorb what little solar energy exists and reach a certain expected equilibrium temperature. Yet, the actual data reveals a surface that is significantly colder than these standard models calculate. This isn't a minor discrepancy, it's a substantial thermal anomaly, a chill that defies the simple laws of thermodynamics and points to hidden, active processes at work on or within this distant world. This thermal mystery forces us to reconsider the very nature of Varuna's surface material. A dark object should, in theory, be an efficient absorber of sunlight and thus should be warmer than a bright, reflective one. The fact that Varuna is both incredibly dark and unexpectedly cold creates a paradox. It suggests that its surface is not simply a passive absorber of energy, but is instead doing something active with the minuscule amount of heat it receives. One compelling explanation is that the material covering Varuna is not just dark, but is also an almost perfect thermal insulator. Imagine a blanket of incredibly fluffy, porous dust and complex organic polymers. a cosmic powder that is excellent at absorbing visible light but is terrible at conducting that captured heat inward. The energy from the distant sun is absorbed only in the very topmost micron of the surface and is then almost immediately re-radiated back into space as infrared energy before it has any chance to penetrate deeper and warm the layers below. This would be like a black asphalt road that somehow feels cool to the touch even under a blazing sun because the heat never sinks in. However, an even more fascinating possibility involves a process of active cooling, a kind of natural refrigeration system operating on a global scale. This theory proposes that Varuna's surface coldness is not just about preventing heat from entering, but about actively expelling it. The key to this lies in the potential sublimation of highly volatile ices. If the weak sunlight is just enough to cause tiny amounts of ices like nitrogen or methane to transition directly from a solid to a gas, the physics of that phase change comes into play. Sublimation is an endothermic process, meaning it requires energy to happen. The ice must draw immense amounts of latent heat from its immediate surroundings to make the jump to a gaseous state. This would act like a massive heat sink, with the sublimating gases actively sucking thermal energy out of the near-surface environment. The resulting gas would then carry that stolen heat away as it escapes into the vacuum of space, effectively giving Varuna a permanent, self-powered cooling system. This would keep the surface far colder than if the world were simply a passive, inert rock, creating the thermal imbalance we observe. The implications of this are profound. If this sublimation-driven cooling is indeed occurring, it means Varuna is not the static, dead fossil we once imagined. Instead, it is a dynamic world, however subtly, still processing energy and actively managing its own temperature. This process would require a reservoir of these volatile ices readily available near the surface, suggesting that despite its dark appearance, Varuna's crust must still contain pockets of pristine, frozen gases. Furthermore, it implies a delicate balance. The same dark tholins that give Varuna its color are efficient at absorbing the sunlight needed to power the sublimation, while the resulting cooling effect prevents the world from overheating and losing its volatiles too quickly. It's a perfectly tuned, self-regulating system that has likely been operating for billions of years, a testament to the complex and unexpected ways that even the most remote worlds continue to evolve and interact with their environment. But perhaps the single greatest challenge lies in the realm of power and communication. At such an immense distance, sunlight is far too weak to power solar panels effectively. A mission to Varuna would require a robust nuclear power source, like a radioisotope thermoelectric generator, not just for electricity, but also to keep the spacecraft systems and instruments from freezing solid in the profound cold of deep space. Furthermore, transmitting data back to Earth across over 4 billion miles would be a test of patience and precision. The signal would be incredibly weak, requiring immense, focused antennas on the spacecraft and the collective listening power of the Deep Space Network's largest radio dishes on Earth. Each precious byte of data, a high-resolution image, a detailed spectral reading, a topographic map, would take hours to transmit, turning the mission's data return into a slow, deliberate trickle of information over many months or even years. The journey to unravel Varuna's secrets would not end with a spacecraft's arrival. It would merely enter its most painstaking and crucial phase, a testament to human ingenuity and our relentless drive to understand even the most remote corners of our celestial home. And so we reach the end of our journey, having navigated the 25 most profound enigmas of this dark, distant wanderer. From its impossibly rapid 6-hour spin and its elongated watermelon shape to the profound darkness of its tholin-coated surface and its unexpectedly frigid thermal signature, Varuna consistently challenges our fundamental assumptions. We've grappled with the paradox of its ancient, weathered appearance alongside evidence of a surprisingly youthful surface, pondered the spectral hints of methane that behaves in ways it shouldn't, and debated the ghostly gravitational tug of a moon we have yet to see. Its wild, non-resonant orbit speaks of a violent past, possibly scattered by Neptune itself, while the potential for residual internal heat and even transient atmospheric whispers suggest a world that is not quite dead but merely sleeping. The conflicting estimates of its density leave us uncertain if it is a fragile, porous snowball or a more solid amalgam of rock and ice, and its resistance to any simple classification marks it as a true individual in the Kuiper Belt's diverse family. What makes Varuna so endlessly fascinating is that it isn't defined by one single mystery, but by the way all these puzzles are inextricably intertwined. Its rapid rotation likely shaped its elongated form, its dark surface contributes to its thermal anomaly, and its unusual composition may hold the key to its potential for sudden outbursts. It is a complex, holistic system where every answer seems to reveal two new questions, a reminder that nature delights in complexity that defies our neat and tidy models. This distant world forces us to reconsider the very definitions of activity and dormancy, proving that even in the most remote and sun-starved reaches of our solar system, dynamic processes continue to operate on timescales beyond human comprehension. Varuna stands as a powerful testament to the fact that our exploration of the solar system is far from over. In many ways, it has only just begun. It represents a frontier of knowledge, a reminder that for all our technological prowess, the universe still guards its secrets fiercely. The greatest chapter in Varuna's story is likely yet to be written, awaiting the arrival of a dedicated interstellar mission that can finally map its terrain, directly sample its composition, and gaze upon its hidden face. Until that day comes, it remains a brilliant and tantalizing point of light in the data streams of our telescopes, a silent enigma that continues to inspire wonder, drive scientific inquiry, and humble us with the sheer scale of the mysteries that await just beyond the known.